Okay, let's talk about rotation about a fixed axis. So if I have a body that's rotating this way with some angular acceleration and has some angular velocity, so our alpha is going to be equal to angular acceleration, and our omega is going to be equal to our angular velocity. We just need to define one more thing. If this is point O, this is going to be this right here is going to be theta, and theta is just going to be our angular position. Now, let's say this is rotating. So at point 0, we're looking at this point right here. At the next point in time, it rotates along this curve to this point. So this d theta is going to be its angular displacement. And its angular displacement is its angular velocity. And so its angular velocity, omega, is going to be equal to this d theta over dt. And we can also say its angular acceleration alpha is going to be equal to the derivative of its angular velocity with respect to time. And a couple of other equations we have for alpha. For its angular acceleration, we know that alpha is going to equal the second derivative of its angular position with respect to time. And alpha is going to be equal to its angular velocity times the derivative of its angular velocity with respect to its angular position. And right here, all 4 of these equations are quite similar to the equations we have for when a body is undergoing rectilinear motion. So here, if omega is going to be equal to our velocity, if alpha is going to be equal to our acceleration, and if theta is going to be equal to our position, we can use we can substitute these in for the kinematic equations that we have, and assuming that we have a constant angular acceleration, so these are only true if our angular acceleration is constant, then we get the equations a final angular velocity is equal to an initial angular velocity plus the angular acceleration times time. The final angular position is equal to an initial angular position plus the initial angular velocity times time plus 1/2 times the angular acceleration times time squared, and we get the final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration times the change in angular position. And this is just like the kinematics the kinematic equations we have for when our acceleration is constant. And again, I'm just going to say these are only valid if the acceleration is constant. If the acceleration is not constant, or the angular acceleration is not constant, then you do need to go about a different method of solving the problem. Okay, so now let's look at the motion of a point P. So if we have a fixed point right here, and this point's fixed. And we're rotating the body, this rigid body, with point P. The point P is just going to be right here, and I'm choosing P arbitrarily like I always do. And the position from the axis to point P, we're going to say is going to be R. So this right here is just R. And we're going to say it has a positive angular acceleration and a positive angular velocity. So this will be alpha and omega. And how do we know this is the positive direction? Well, what I'm doing is I'm assuming a conventional XY coordinate system. So Y is pointing positive up and X is pointing positive to the right. And we figure out what our positive Z direction is and what the positive direction that our angular velocity is by the right-hand rule. So if you point your fingers towards the x-axis, so your finger is in this direction, and you curl them up towards the y-axis, your thumb is going to be pointing back towards you. And this shows you the positive angular velocity direction, and the way your thumb points is the positive z direction. So that's how we figure out what our positive directions are and what our positive angular velocity and acceleration directions are. And because it has an angular velocity and acceleration, point P is going to look like it moves on this circular path. I'm going to make this a different color to distinguish it from our coordinate axis. But point P looks like it moves on this circular path right here. And at this point, it has a velocity, which is always tangential to the path it's moving. So here's its velocity. And because it has an angular acceleration, it's going to have an angular acceleration, a tangential acceleration this way. And it's going to have a normal acceleration, which points back in towards the circular path. And here's its normal acceleration. So the magnitudes of all these values, the velocity, the tangential acceleration, and the normal acceleration, I'm just going to give it to you. I'm not going to derive it out. Maybe I'll do another video on where it comes from, but it would take a while. But the velocity, v, is equal to this distance r times the angular velocity. This tangential acceleration, at, is equal to this distance r times the angular acceleration, and the normal acceleration is equal to omega squared, so the angular velocity squared times r. There's one more thing we can sort of get from this this picture. If we define this right here as an angle, we can figure out how far P has moved. Assuming it starts on the x-axis, we can say that the distance it moves, s, is equal to r times theta. So this is good for this sort of 2D sense. But what happens if something's moving in 3 directions? And that's the case sometimes. So it gets a little more complicated when that's what's happening. All right, I just needed to stop that to draw a good picture that I can use to show you the vector formulation of all this stuff. So if we have this z-axis that we're rotating around, and I've just put these on the x, y, z axis to make it easier to visualize, we're going to have a angular velocity, omega, and an angular acceleration, which is alpha. if we define the position of point P with a position vector, so this right here is going to be our position vector r, we know that point P is going to have a velocity that is tangential to the path it's traveling on and is 90 degrees from this position vector r. So right here we have a velocity, and here's its velocity vector. And its velocity vector is 90 degrees with its position vector. Now, in addition to a velocity, it has this angular acceleration, so it's going to have a tangential acceleration. We're going to show that like this. And it's also going to have a normal acceleration. And why does it have a normal acceleration? Well, it's moving on a curved path, so it has an acceleration that points back in towards the path of the circle. It's towards the center of the circle that it's moving on, and that's its normal acceleration. So let's try to come up with expressions for velocity and our accelerations. So our velocity, our v vector, is going to be equal to the cross product of omega and the position vector, the angular velocity and the position vector. And if we look at this, this makes sense. We know that the cross product of two vectors is going to give us a third vector that is orthogonal to both of those. So if we have our angular velocity, which is just in the z direction, and we have this r vector, this position vector, which is just in our x direction, the velocity is going to be just in the y direction. And I know it doesn't look completely parallel, but I'm telling you this is just in the y direction. So this makes sense if you think about it that way. The velocity is going to be orthogonal to both the angular velocity and the position vector. So now let's look at what our acceleration is. Our total acceleration is going to be our tangential acceleration plus our normal acceleration, and our tangential acceleration is this right here. So using the same logic, it's going to be equal to the cross product of the angular acceleration with the position vector. And again, since a cross product gives you an orthogonal vector, or cross product of two vectors gives you a third vector that's orthogonal to both the vectors that are being the cross product of. Here is the axis that the angular acceleration is acting on, and here is it's the z direction. Here is the axis that the position vector is acting on. It's the x direction. So our tangential acceleration has to be in the y direction. Now, the normal acceleration is a little trickier. The normal acceleration is going to be equal to this expression. It's going to be equal to the angular velocity crossed with the angular velocity crossed with the displacement. And let's look at this for a second. Let's look at this part right here. This is saying that it's the angular velocity crossed with this r position vector, so we get a vector that's pointing in the tangential direction. So we get a vector that's pointing in the this y direction. So I guess since we're doing vectors, I'll call it our j. We have a vector in the j direction. Now we're going to have this vector right here crossed with the j direction. So if we have something in the j direction crossed with something in the z direction, we're going to get something in the x direction. And if you do the cross product out, you're actually going to get something in the minus I direction. So that makes sense, right? We're pointing away from our positive, we're pointing in the negative direction, and this makes sense. So this is what we're going to get. We'll see plenty of examples of ij's and k components later, but this is what the expression for the normal acceleration is. So our total acceleration is equal to this alpha cross the position vector, so our angular acceleration plus the position vector plus this expression for the normal acceleration. Now this can get simplified a little bit, and I'm not going to go through the math. I think I will make another video going through the math of all this, but just trust me on this. The acceleration goes to the angular acceleration crossed with the position vector, and this becomes a minus omega squared times the position vector r. And this becomes what our acceleration is equal to. So what do we have? We have in a scalar we have scalar equations, and these scalar equations are that our velocity is equal to omega times r, this distance r, that the tangential acceleration is equal to alpha times r, and the normal acceleration is equal to omega squared times r. And we have a vector formulation that our velocity is equal to omega, which is the angular acceleration, cross the position vector. Our tangential acceleration is equal to the angular acceleration crossed with the position vector. And we have a normal acceleration that is equal to minus omega squared, so minus the angular velocity squared times the position vector. And one important thing to note is this omega squared right here, this right here is not a vector, it's a scalar. So this right here is a scalar, not a vector.